Hello, research design and analysis students. Today we're going to be talking about distributions, specifically histograms for interval or ratio data, and how to tell if that group of data that you have is approximately normal, which is a nice bell-shaped curve, kind of balanced and symmetrical on both sides, like a nice bunny slope if you were thinking about a ski hill instead of a black diamondback kind of mountain. And there are a couple of different ways we can look at a distribution or spread of data and figure out if it's nice and sort of normal, nice rolling hill, or something different. Maybe it's really tall and spiky, leptokurtic. Maybe it's really platykurtic, like a platypus tail, very flat. Maybe it's skewed or wonky to one side or the other. Right? So if we don't have that nice hill, what's called mesokurtic, approximately normal distribution, and we have some other kind of lumpy, sideways, abnormal shape, it will affect which statistics we choose. So we would want to figure out, in looking at a distribution of data, if it's approximately normal or not, so we know what statistics to run. All right? So I'm going to zip up to the corner and show you that there are actually 3 different ways that you can practice figuring out if a distribution is approximately normal or not, going from the most flexible way for beginners to get started, which is looking at the graph and eyeballing it to say, does that look normal, tall, slanted, etc. We can also run some descriptive statistics, which allows SPSS to give us some numbers to figure out if it is if the kurtosis is not normal, or the skew is kind of lumpy, or both. And there's a specific test we can use that looks at skew and kurtosis together to make the decision about whether something is normal. Now, first off, we're going to use the candy data set that we have been practicing with at other points in our semester, where we gave people bags of Skittles or M&Ms and asked them to record the number of candies in each bag that were red, yellow, orange, or green. The first way that we could look at skew and kurtosis is to go to Graphs, and Legacy Dialogues, and Histogram. Remember that a histogram is only used for interval and ratio data. SPSS will make one for nominal ordinal data, but it won't be appropriate. So we want to go ahead, and you will start out with it looking like this, to then say, all right, let me look at the spread of data for this variable, and we'll start with our red Skittles. And we put that variable in here, and we ask it to put a normal curve on, so we could see what a normal hill would look like if our data was pretty regular. You can also use the title button to go ahead and add your title here, number of red Skittles per bag. Or I will show you in another screencast how you can do tweaks and modifications to graphs after you've already made them. So variable, curve, title, and click OK. And you will get a graph then that shows the dispersion or variability or distribution of scores for red Skittles. Now, if we had a normal curve, it would look kind of like this. And so if we see any values that are significantly off of that curve and don't seem to match this, imagine this is like an outline. If there's something that sort of doesn't fit the outline and goes outside the lines, then we might say that that's not quite normal. In this case, we've got this spike that's falling taller than this curve, and when we've got a spike of scores that's taller than the curve, we have what's called a leptokurtic data set. Lepto meaning leaping. All right, so we've got kind of a leap here. This hill is a little steep, so it's not approximately normal. So eyeballing it by looking at the histogram itself is one way that you can try to figure out if you have a normal distribution. A second way that you can do it is to go to Analyze and Descriptive Statistics and Explore. And we can then ask, get some numbers. Let's use red Skittles again. We're going to put that in our dependent list. That's the factor we want to look at. And it will, by default, give you some statistics and some plots or graphs to show you what this variable looks like. So if you click on statistics to check it out, it's going to run a batch of descriptives. That's mostly what we need. We don't need to change anything else. It will also do plots, by default giving you a stem and leaf plot, maybe, which is kind of like a histogram turned 90 degrees sideways. We can go ahead and ask it for a histogram. And it will also give us a box plot, which is based on the median instead of the mean, to see how those scores spread around the middle point. So I would suggest adding histogram. Box plot's fine, stem and leaf's fine. Continue. And then if we take a look at options, we don't need to change anything there. So we made sure with plots that we asked it to give us a histogram. When you click OK, you'll notice you got the histogram, which looks kind of like the other one, but it doesn't have a normal curve or outline guide on top of it to help you eyeball it, which is why I like doing it up here. But in the descriptives, not only does it give us estimates for our measures of central tendency and variability, like our mean, our median, standard deviation range, interquartile range, but it also gives us indicators of skewness and kurtosis. Right? Skewness is about how much it's leaning to one side or the other, especially if it's being pulled by an outlier or extreme score. So skewness is about it being off-center. Okay? Kurtosis is about the tallness of the shape, whether it is tall and leaping or kind of flat or a nice hill in the middle. If either of these variables, numbers right here, is pretty big, that would incline us towards saying, yes, we've got skew, or yes, the kurtosis is different, so it's not normal. Now, some authors have some statisticians have different estimates for how big this needs to be before we consider it not normal. I've seen some textbooks use a value of 2. I've seen some use 3. I've seen some who are really picky use 3.29, which is, I think, the one mentioned in my PowerPoint. So these ones here, because they're smaller than 2, are a little bit, but it's really not too bad. So if we use this standard to tell if our distribution is not normal, these values are pretty small. Okay? We could probably get away with saying it's approximately normal. Notice there's no hard and fast rule. When we looked at it just by the graph, we said it looked a little leptokurtic, and it is still, okay? But it's not awful. So this would be the kind of case where if in your homework for me, you either called it normal or you said it was leptokurtic and you gave me how you made that decision, I'd probably give you credit either way. Other graphs that we'll look at this semester, it's clear, right? It's normal or it's not. The last way that you can look at skew and kurtosis to get a number, like just tell me, Dr. Wickline, is it too far? Is it too messed up? If that's how you like to approach this task, you can go to Analyze and Non-Parametric Tests. A couple of steps here. Non-parametric, Legacy Dialogues, and One Sample KS. One Sample KS stands for Kolmogorov-Smirnov test. Smirnov, named after the researcher, not the vodka. But what's cool about a Kolmogorov-Smirnov test, again, named for both people that put the work into making this formula, is that the letters actually line up for what you're looking for too. We're looking at kurtosis and skew, so we want that one with KS in it to figure out if the distribution we've got is lumpy or not. All right, so I'm going to put in my red Skittles again. I'm going to throw it over here on the left. So we're going to test whether that is normal or not, so don't mess with these other buttons. Just leave it on normal. And you don't need anything over here in the exactor options. That's for more complicated stuff that you guys aren't ready to do yet. So once you've got the variable, click OK. And you will get output that looks like... Oh, wait a minute. I got everything but red. That's because I was playing with this before. Let's try it again. Non-parametric, legacy dialogues, one sample KS. When you reset it, they all start out over here. Sorry. So I'm going to put that red Skittles back in. And we're going to take a look at what we got. There we go. There's our red Skittles. So it uses the Skittles to use the mean and standard deviation to look at the extremes and come up with a test value to tell you, is it normal or not? Now, this test statistic, the bigger it is, the smaller the significance value will be. We've just started talking about significance value. Remember, it's a measure of probability or likelihood. And we want that significance value to be small. That means something's going on that we're interested in. It probably didn't happen by chance. It's something that tends to stand out. So when this value, the significance value, is less than 0.05, that means ding, 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 winner, winner, chicken dinner, you've got something. Now in this case, if we're looking for non-normal, having that significance means this distribution is not normal. We were comparing it to normal, we got something else, right? So if you were using the Kolmogorov-Smirnov test and you got a little value in here, less than 0.05, that means the distribution is not normal. Then you'd have to look back at it and try to figure out, well, is that because of skew or kurtosis or both, right? You can actually have something that only fits one or the other, or seems to be wonky on both fronts. All right, so to recap, we learned how to create a histogram and eyeball it with that normal curve in the graph function to see that something is a little bit off of normal. We ran descriptives and looked at these values here. And again, if these are bigger than 2, definitely bigger than 3, then our distribution is not normal. So this one's a little off, but not too bad. And then if we use the Kolmogorov-Smirnov test down here, this does look like it's far enough off that we should call it not normal. All right, so hopefully one of those 3 ways is how you can decide when I ask you, tell me about skew and kurtosis, to figure out what that distribution looks like. Thank you.